Hello everyone. Today we will discuss about quantifiers. A sentence that includes free variables is called a predicate. If we insert values into the free variables, then we obtain a proposition. Let's see an example. Let's plug some values into a free variable of a predicate to get a proposition. Let's consider the predicate p of x to be the sentence x is a prime number. Here are a few values of x that we can insert for x. If we put 2 in, we get the proposition 2 is a prime number, which is true. If we put 3 into x, we get 3 is a prime number, which is also true. If we put 10 into x, we get the false proposition that 10 is a prime number. We can also put 5657 into x to get a true proposition. And we can even put a value like car into x to get the proposition car is a prime number, which is false, because car isn't even a number. To avoid having weird elements placed into our predicate, we often set a universe of discourse first for our predicate variables. In this particular example, let's set the universe to be the set of counting numbers. And then consider the predicate with 3 free variables. It's given by the sentence x squared plus y squared equals z squared. And now let's consider a few triples of values for x, y, and z. So when x, y, and z are 2, 3, and 9, we get 2 squared plus 3 squared equals 9 squared, which is a false proposition. When x, y, and z are 3, 4, 5, we get the classic Pythagorean triple 3 squared plus 4 squared equals 5 squared. We can get the other one, 5 squared plus 12 squared equals 13 squared, which is also true. And we can get a proposition like this, which we have to check to see if it's true or false. An alternate way to get propositions from predicates is to add quantifiers. So let's investigate the existential and universal quantifiers. Given a predicate of the form p of x, we can create a proposition by quantifying the free variables. That is, by asking how many variables make the predicate true. The existential quantifier is denoted by a backwards e. And the proposition there exists x, p of x, is true if there exists at least one value from the universe making the predicate true. We read this as there existing x such that p of x is true. The existential quantifier can be thought of somehow as the infinite or over the universe, because we're just looking for one possible value that makes the predicate true. The universal quantifier, on the other hand, written by an upside-down a, is true if every possible value of x from the universe makes the predicate true. For this one, we say p of x is true for all values of x. Just like the existential statement, we can think of the universal as being an infinite and over our universe. We need all of the propositions to be true, no matter which value of x we plug in. Let's see a couple of examples of predicates with quantifiers creating propositions. Consider the predicate p of x given by the sentence x is an odd square number over the universe of counting numbers. If we apply the existential quantifier to this predicate, we get that there exists at least one odd square number. If we think carefully about this, we know this is a true proposition because we can use x equals 9 as our existential value. P of 9 is true, so at least one value is true. Likewise, if we add the universal quantifier, we see that this translates to every number is odd and square. This is false because many numbers make p of x false. They don't all make it true. For example, x equals 3, x equals 4, and x equals 6 all make some part of the proposition p of x false. Try it yourself. Consider the predicate q of x given by the sentence, if x is even, then x squared is even, over the universe of counting numbers. What can you say about the quantified statements, there exists x q of x, or for all x q of x?
About combining 2 or more quantifiers together, and the order of quantifiers sometimes matters when there are multiple quantifiers of different types, their order matters. So let's see an example. Suppose that the universe is a collection of objects 1, 2, 3, 4, and 5, and the following grid gives the truth values for a proposition p, x, y, where x is the row and y is the column. Suppose that we populate this table with the following truth values so that we now have a full grid of information about the predicate pxy at the various values of x and y. Let's start off by investigating the proposition for all x there exists a y such that p of xy. The universal is attached to the x variable, so we see that for every single row, we must find at least one column with a true value. Row 1 has true in column 1, row 2 has true in column 1, but row 3 we have to go to column 3 before we find a true value. Row 4 we go to column 2 to find a true value, and row 5 we find a true value in column 1. Since every single row has at least one true value, we see that the proposition for all x there exists a y p of xy is true. Let's switch up the order of the quantifiers and see what happens now. So there exists a y such that for all x, p of xy. This one says that we need to find a column where every single row is a true value. Well, this doesn't happen in column 1, there's a false value. In column 2, the first entry is false, so this doesn't satisfy the condition. In column 3, the first entry is false, so this doesn't satisfy the condition. But in column 4, if we look carefully, every single entry in every row is true. We don't even need to check any other rows because this is an existential statement. We have found one column where every single row entry is true, so this proposition is true. Just to pound this home though, these two statements were true, but for very different reasons. So let's look at the proposition for all y, there exists in x, p of xy. This says that if we look in every column, there better exist one true value. So if we go column by column and look for a true value, we'll see if we can find one in every single column. The first column has a true value in position 1, the second column has a truth value in position 4, the third column has a truth value in position 2, the fourth column has a truth value in position 1, and the fifth column has a true value in row 1 as well. Since there's a true in every column, this proposition is true. Let's switch the order of the quantifiers though to get the proposition there exists x such that for all y, p of xy. This means there is a row such that every single column in that row is true. Well, if we go row by row, we will see that every single row contains at least one false statement. So there is no row where every single entry is true. Therefore, this proposition, there exists x, such that for all y, p of xy must be false. Just to recap, the first two propositions were both true, even though the order of their quantifiers were different, but they were true for very different reasons. The second two quantifiers listed were actually different. One was true and one was false, so the order of the quantifier clearly matters.